We take up this problem of problem number 78 of your textbook. Here is a diagram is very clear. Figure shows a rough track. Mind it, it's a rough track. That means this track has got a friction so that the ball which is rolling over the track does not slip. I repeat, it does not slip. Only it rotates. A portion of which of this track is in the form of a cylinder of radius r, like this. At what minimum linear speed should the sphere of radius r be set rolling on the horizontal part so that it completely blows round the circle of the cylindrical part? Okay. What should be the minimum speed of this small roller? Let us consider the minimum speed, V minimum. Let us say this is V. Let us say this is V. Now, this roller, this small ball will at some time come here. And then if it has got enough kinetic energy, it will follow this track and it will go to the top here, like this. Now, it is needless to say that once it can reach the top, it will evidently follow the track and come down and make a complete circle. So, actually, instead of calculating the complete circular path, you have to calculate so that it reaches the topmost point at least. Say this point P, say this point Q. So we have to see that the small sphere, reaches the point Q. So we have to, I write it here, we have to ensure that the small sphere reaches the topmost point Q. That is, we have to ensure. Now, to start analyzing the problem, let us consider when it reaches the topmost point Q, it will have a linear velocity, rather its center of mass will have a linear velocity towards the left. And let us consider this linear velocity is V1. Right? So we write, say, when it is Q, not its, I write its reaches Q, center of mass has the linear velocity is equal to V1. If its linear velocity is V1, then the condition of the sphere sticking to the circular path is always, we know, from the chapter of I think it was chapter of circular motion, that mv square by r must be more than mg because it has a downward force of mg. The the condition of the sphere sticking to the cylindrical path is m v1 square by the radius of the circular path. Now, radius of this circular path here, it is equal to capital R minus small r. This radius is equal to capital R minus small r. What is small r? We have considered small r is the radius of the small sphere. mv1 square divided by capital R minus small r must be more than equal to mg. Here I write taking small r is equal to radius of the small sphere. Is the radius of the small sphere. Right? Now, in the limiting case, this is equal. So, in the limiting case, mv1 square by capital R minus small r is equal to mg. From here, we get this m and m gets cancelled. From here, we get v1 square is equal to g capital R minus small r. This is one condition. We remember this condition. Then we go to the point P. Then you go to the point P when the ball is at point P. So we write when the ball is at P. When the ball is at P, its total kinetic energy is its rotational kinetic energy plus its linear kinetic energy or translational kinetic energy. When the ball is at P, its total kinetic energy is equal to, it has a rotational kinetic energy is half I omega square and a translation kinetic energy of half mv square is half its mass we have considered m, say its mass m, say mass m. Mass is equal to m. Because mass was not given, so we have considered mass m. So total kinetic energy half m into its center of mass has a velocity v by the problem. So half mv square, and this velocity v we have to find out. Half mv square plus plus half I omega square. Omega is the angular velocity of this object at that time. This is equal to half mv square, half mv square plus half I. I is a sphere, so its moment of inertia is 2 by 5 m, again mr square, multiplied by omega square can be replaced by v square by r square. If we do that, then this is equal to half mv square plus here this 2 and 2 gets cancelled, r square gets cancelled, so 1 by 5 mv square. 1 by 5 mv square. This is equal to LCM of 2 and 5 is 10, then we have 5 plus 2, 7. 7 by 10 mv square. Now, so actually, whenever a body or a sphere of radius r moves, rolls on a rough surface with a linear velocity and results in a linear velocity v, its kinetic energy we find is 7 by 5 mv square. 7 by 10 mv square. In fact, it's a relation which is useful if you can remember. Whenever a sphere or solid sphere rolls on a rough surface, pure rolling, then it has got a kinetic energy due to rolling, and also it's the kinetic energy because its center of mass moves forward, and the total kinetic energy is 7 by 10 mv square. If we apply the same concept to the ball when it reaches Q, then at that point its kinetic energy is 7 by 10 mv1 square, because we have considered its linear velocity at that time is v1, right? So, so we do like this. Similarly, kinetic energy when it reaches Q is equal to 7 by 10 m v1 square. Why we really reduced this expression? Because the difference of kinetic energy between P and Q will be equal to the potential energy gained. That is a very simple idea, nothing else. Now, what is the potential energy gained by the ball when it reaches from P to Q? Potential energy gained by the ball, potential energy gained when it reaches from P to Q is equal to mgh is mg, and what is the distance from here to here? Distance between the two center of masses. Distance from here to here is 2r minus 2 small r. So this is 2r minus 2 small r. This is equal to 2 mg, 2 mg capital R minus small r. So obviously, what do we find? Now here, I'll extend this a little further because V1 was already obtained. V1 square was already obtained here. V1 square is GR minus R. So here I go a little bit one step further. Is 7 by 10, 7 by 10 M V1 square is G capital R minus small. Now, obviously, kinetic energy at the bottom, is 7 by 10 mv square. So, let me write a sentence, additional sentence here that will be useful to you. Kinetic energy at kinetic energy at T will be equal to kinetic energy at Q plus potential energy gained from T to Q. Knowing that, we can write kinetic energy at P is given at 7 by 10 mv square, 7 by 10 mv square is equal to kinetic energy at Q is 7 by 10 mg capital R minus small r, 7 by 10 mg capital R minus small r plus potential energy gained is 2 mg capital R minus small r, 2 mg capital R minus small r. From here, we get 7 by 10 mv square, 7 by 10 mv square is equal to, here 7 by 10 plus 2, it makes 27 by 10. 27 by 10 mg capital R minus small r. So this 10 and 10 gets cancelled and M gets cancelled. So V square equal to 27 by 10. So V square equal to 27 by 10, 27 by 7. V square equal to 27 by 7 GR minus R. G capital R minus small r. So our required value of V is equal to 27 by 7 G capital R minus small r whole thing under. So this is the minimum value of velocity V. It is not velocity of rolling. It is actually linear velocity attained by the center of mass of the small ball due to its rotation. It must be this value, under root 27 by 7 capital G within bracket capital R minus small r. Now we go to the next question.